Hi everyone. In this video I will be demonstrating an application of polynomial regression using SPSS version 28. And in particular I'll be focusing in on a situation where I have a single independent variable and a single dependent variable. Now before I get started, I do want to mention that the data set that you see on your screen you can download a copy of by following the link that's provided underneath the video description. So feel free to download a copy of the data to follow along. So let's go ahead and get started just by considering the data itself. We have two variables in our data set. We have a measure of student interest and a measure of student achievement. Now let's say that I want to model the relationship or the predictive relationship between interest and achievement, where interest is the independent variable and achievement is the dependent variable. Well, I can easily do that in SPSS by going through the following menus. Basically go to Analyze, Regression, and then go down to Linear here. And what we would do is move the interest variable to the block 1 of 1 here, and then the achieve or the dependent variable to the dependent box, and click on OK. So as we're looking at our output, I'll just kind of draw your attention to several different things, mainly because I'm kind of assuming that by this point, if you're studying polynomial regression, that you have some background in simple linear regression and multiple regression. But as we're looking at our output here, you can see in the coefficients table, we have the intercept for our model. The intercept is just the predicted value on y when x is equal to 0. And our interest variable right here, you can see that we've got our regression slope. So again, this is our intercept that I'm circling right here, and then the regression slope of 31.945 that you see right here. And because that regression slope is positive, that's indicating that we have a positive relationship between interest and achievement. Now whether that's a significant relationship we haven't gotten to yet, because that's where the significance test comes into play. But nevertheless, because there's a positive relationship, or at least what we think is a positive relationship, that would basically indicate that higher scores on interest would be associated with higher scores on achievement, lower scores on interest would be associated with lower scores on achievement. And the actual number, the numeric value that's given of 31.945, it would be interpreted as meaning that for every 1 unit increase on interest, there's an increase of 31.945 with respect to the predicted values on y, or basically the predicted change on achievement. Now, when we look at the significance test result right here, you can see that's printed out. We have statistical significance. So that would be an indication that there's a significant relationship between interest and achievement. Just keep in mind that the regression results that are printed out in SPSS by default are two-sided tests. So just kind of keep that in mind. As we go up to the model summary portion, I do want to draw your attention to the R-squared value of 0.703. If you multiply that by 100%, that we would basically interpret this as an indication that interest is accounting for about 70.3% of the variation in achievement. And then when we look at the ANOVA summary table right here with the F-test result, I'll just kind of note that basically this result right here is redundant with the two-sided test that's given below. So there's not a whole lot else to kind of say at that point with respect to the ANOVA table that's printed out. So the thing to keep in mind at this point is that when we specified our model, we were essentially assuming that the relationship between interest and achievement is best described as linear, or in other words, that a linear functional form best accounts for the relationship between the two variables, or that's the best way to kind of capture that relationship. But it is possible that when you're running a regression analysis, that if you specify a linear functional form but the relationship is actually nonlinear, then you can end up underestimating the relationship and not doing an adequate job of describing how those two variables are related to one another. So this is kind of where polynomial regression ultimately kind of comes into play, where we try to capture any kind of curvature in the data by specifying an equation such as a polynomial equation. So let's go back and look at our interest and achievement variables. But before we kind of get into specifying models and so forth, let's visualize the relationship. And so to do that, we're going to go to Graphs and go down to Legacy Dialogs and then click on Scatter Dot down here. We'll click on Simple Scatter and then Define. I'm going to reset this, and we're going to move our interest variable over to the x-axis, achievement to the y-axis, and we'll click on OK. And so as you can see with our scatter plot, the data doesn't seem to follow very clearly a linear pattern, but rather it looks like there's some curvature in the data. And in fact, I can kind of draw this out kind of freehand, if you will, right here, and trying to kind of follow the data. And you can see that it looks like there's some curvature. Now we can kind of get a better picture of things by just double clicking in this box. And if we go up to Add Fit Line at Total, what we have is a situation where the program kind of by default tries to fit a linear model to the data. And so you'll see that by default it starts out with linear right here, and the equation that's given down here is actually the same equation that we had generated previously when we ran our simple regression model. And so you'll see that we've got x times a regression coefficient then plus the intercept. So that's what you have right there in that equation. And you'll also see that we have an r-squared value of 0.703. So this is literally the program's kind of default effort, if you will, to fit a linear function to our data, and it kind of misses out a little bit. It does a pretty good job because the r-squared value is still pretty high, but it's not perhaps quite as good as what we might have if we tried to capture that relationship using some type of nonlinear form. So now let's click on Quadratic. So if we click on that and then on Apply, you'll see that now the fit line has a curve in it, and it seems to follow the data much better. And so as you're looking at this, you can see with this particular equation that's given, this is essentially following a quadratic form. So, with a quadratic equation, if you're familiar with, if you go back to your old algebra days, we could say that y is equal to ax squared plus bx plus c. And as you can see right here, we have an x squared variable that's created. So in other words, the square of x times the regression coefficient that's given right there. That regression coefficient is essentially equivalent to the a in that quadratic formula. Then you've got x times the regression slope, and that regression slope right there is equivalent to the b. And then the c is for the intercept is equivalent right there in the equation. So at any rate, you'll see that because that line is doing a better job of fitting that data, you can see the r-squared value has now increased from 0.703 up to 0.906. So in other words, we're doing a better job, it looks like, in terms of fitting the data. So by if we were to add in the square of our x variable into the model as a predictor. Another possibility is that maybe a cubic functional form does a better job of fitting the data. So if I click on cubic and then on apply, you can see now that our equation kind of changes a little bit more by adding in the cubed x variable. We still have the squared x variable and then also x right here, and then there's again our intercept right here. So in other words, we've added in two additional terms over the linear model in order to capture this relationship. And so as you can see, it looks like maybe that line does a little bit better job of fitting the data, maybe just a shade better than the quadratic. And so you can see that the r-squared seems to increase from 0.906 up to this 0.921. So in other words, we can account for a little bit more variability by perhaps adding in that quadratic or modeling as a quadratic. So the thing to keep in mind is, at this point, what we've done is we sort of visualized our data, and we were able to kind of graph it out and visualize possible possible functional relationships between our interest variable and achievement. But we still want to test out these different models to see perhaps which one of them does the best job of fitting the data while also remaining reasonably parsimonious. And so that's where, in particular, where polynomial regression becomes particularly useful. So I'm going to walk you through some steps for carrying out the polynomial regression in SPSS. But before I do that, what I want to do is to kind of walk you through the strategy. So here you can see what I have are three models that are represented, and these are literally the same three models that we were just looking at through the graphing option in SPSS. So you'll see that the first model that we have right here, we have student achievement is a function or a linear function of interest. So the assumption when we ran that simple regression was that interest is a linear predictor of achievement. And you can see that when we ran our analysis, we estimated the intercept and we estimated the regression slope for interest. And we ended up generating an R-squared value that was equal to the 0.703. So I'll just say R-squared is equal to 0.703 right there. Now, the next model, which we haven't officially run, but we allowed the program to generate the estimates for us just as we were doing our graphing. You can see that achievement is still a function of an intercept and then a slope times our interest variable, but then we're adding in another predictor, and that is interest squared. So we're estimating then, in this case, we're estimating 3 parameters instead of 2. We have the intercept for our model, we have our regression slope for interest, and then we also have the regression slope for our squared interest variable that you see right here. And so you can see it kind of visually over on this side of the screen right here. The R-squared value that we saw when we generated that equation using the graphing approach was 0.906. So I'll just say 0.906 right here. So it's a little hard to see that 9. Okay, so then the last one we had achievement is a function of interest, but also we're adding in interest squared and also interest cubed. So we have our intercept that's being estimated, the slope for interest, the slope for the interest squared, and then also the slope for interest cubed. And by the way, this should be reading as B3 or B sub 3 right there. So now we would have 3 predictors within this model. So you can see that the first model is essentially a simple linear regression. The second model is a multiple regression where we're incorporating interest and interest squared. And then the third model is also a multiple regression where we're incorporating interest, interest squared, and interest to the third power. And then if we look at the R-squared value, again, kind of thinking back to what we generated through the graphing function, we had R-squared that was equal to 0.921. So in terms of making a decision about which functional form we want to assume in our data, then what we want to do is kind of go through a model comparison approach. So in other words, we can compare model 1 with model 2 and see if the change in R-squared between those two models is large enough that that would lead us to prefer model 2 as opposed to model 1. If the change is not really considered to be significant, then we would probably stick with model 1. But if the change is significant, then that would lend support for a preference for model 2. So we would do that change right there. So we have the change from model 1 to model 2, and then we also would be testing the change in R-squared between model 2 and model 3. And so again, the basic idea is we want to do the best job we can in terms of accounting for variation, but we also want to be reasonably parsimonious with the final model that we select. So for the change in R-squared between model 2 and model 3, if the change is significant, then that might lend support for assuming a cubic functional form between interest and achievement. And if the change in R-squared between model 2 and model 3 is not significant, then that would lend greater support for approaching or assuming that a quadratic form best describes the relationship between interest and achievement. So with that in mind, we're going to go back into SPSS and go through these steps. So here we are back in SPSS, and we have our interest variable and our achievement variable once again. And now what we need to do is we need to create a squared interest variable and then also a cubed interest variable for inclusion in our regression analysis. So to accomplish that, what we're going to need to do is to use the transform function up here, and we'll go into compute variable. But before we do that, it's generally recommended that if we're going to be creating these terms, what we need to do is to mean center this interest variable right here. So there's a nice discussion on it in Cohen's book, Cohen et al.'s book from 2003. So I'm not going to go into the details on that, but this is just a recommendation that they provided, and it's also echoed by other authors. So what we're going to do is we're going to start by centering this variable at its mean. So to do that, we need to actually obtain the mean for that variable. So I'm going to go to Analyze, Descriptive Statistics, and then go down to Descriptives. We'll move the interest variable over to this box and click on OK, and we get the mean, which is 5. So at this point, now what we'll do is we'll go up to Transform and Compute Variable, and let me just kind of reset this. So in the target variable box, we're going to start off by squaring the centered interest variable, but actually before we do that, we just need to mean center the interest variable. Sorry about that. So we'll type in a target variable name. So this is any name that we want to give it. So there's nothing special about what I'm about to do. So I'm going to type in interest underscore C because I want to denote, at least to myself, that I've centered this variable and have that in the data set. So in the numeric expression box, I can either double click on interest and move it over, or I can just type it in. I'll just go ahead and type it in, interest minus 5. So this is going to mean center the interest variable and basically creating a new variable that is the mean centered version of the original. So now I'll click OK. And so I have this variable now included in my data set. So there's a centered interest variable right there, which again was centered at 5. Next, I want to square this centered variable. So I'm going to go back to Transform and Compute Variable, and I'm going to create a new target variable. I'll just I'll just type an underscore, and then I'll type SQ for squared. And I can do this in a couple of ways. One way I could just, if I didn't want to delete this, I could just type, create parentheses around interest minus 5, which is again the mean centered variable, and then I can type 2 asterisks followed by a 2, and that's instructing SPSS to square that centered variable. So I could either do that, or if I just want to use the original centered variable right there, I can do that. Either way works fine. So at this point, I'm going to click OK, and so now I've got a new variable in my data set, which is the centered interest variable now squared. So next, we're going to create our cubed variable. So we'll go back to Transform, Compute Variable, and again, this is just kind of arbitrary naming, but I'll just type in CU right here at the very end, just to denote that we are cubing this variable. We're going to stick with our squared interest underscore C variable inside the parenthesis, but then instead of having 2 asterisks and a 2, we'll have 2 asterisks and 3 to denote that we are cubing this variable. So we'll click OK, and so now we've got all 3 of our variables that we're going to be using in our polynomial regression. So next we're going to go to Analyze, Regression, and Linear. And by the way, there is actually an easier way of doing this, and I'll show you in a little bit using the curve estimation approach. But a lot of this is just to kind of set the conceptual foundations of what this process entails. So we're going to click on Linear right here, and I'll just kind of reset it, and we'll move achievement to the dependent variable box. We'll move our centered interest variable to block 1 of 1. We'll click Next, and then we'll move our squared interest centered interest variable over to block 2 of 2. Then Next, and we'll move our cubed centered interest variable to block 3 of 3. Then we'll click on Statistics, and then we want to make sure to click on R-square change, because we want to look at the change in R-square from one model to the other and have tests of that change. So we're going to keep things simple. I'm not going to select anything else, but I will click on continue and then on OK. And so now looking at our output, you can see up here variables that are entered at different steps. So you got the centered interest variable for model 1. We're adding in the squared interest variable in model 2, and then the cubed interest variable in model 3. So we're adding those in a sequence. So this is, basically hierarchical multiple regression using these various versions of the interest variable. So we'll start off looking just at model 1. You can see there's our R-square value. It's the same as what we had before. You can see the ANOVA results for model 1. All that's exactly the same as before. And then if we scroll down and look at the coefficients table, once again, all of these results are the same as what we had earlier on when we ran our simple regression. Then we've got for model 2, there's the R-square value, which is 0.906. There's the f-test for that particular model. And if we scroll down a little bit further, you can see that we have our regression coefficients for model 2. So those, this is all that information for that particular model. And then finally, when we look at model 3, you can see the R-square is 0.921, which is what we had found before. There's the f-test for that particular model, and then when we scroll down, again, we've got our regression results for that third model. Now, if we go back up and look at our model summary table, included in this table are R-squared change values. So you can see the change statistics right here, and in this column are the R-squared changes. So you'll see that the R-squared change for model 1, it's given as 0.703, and you'll see that all of these results right here are essentially mimicking what we had for R-square right here and these results. And that's basically just comparing this model that contains the centered interest variable against a null model. So in large part, that information is redundant with what we've already kind of been talking about. So it's not helpful. It doesn't add any value in terms of your interpretation. Now, where the R-squared change becomes important is now when we look at the change in fit between model 1 and model 2. So you can see that the R-square for model 1 was at 0.703. For model 2, it's 0.906. So the change is 0.203. So in other words, we account for an additional 20.3% of the variation in student achievement by virtue of adding in the square of that centered interest variable. And we have an f-test for that change. And so you can see right here that the p-value that's given is indicating that the change in fit between model 1 and model 2 is statistically significant. And that's going to lend support for sticking with, at least in between those two models, sticking with the second model. You'll also see, again, here's your f value and then your degrees of freedom for that particular model. Then, or for the test of the change, excuse me. Then what we have is we've got model 3, and we've got the R-square value here of 0.921. So the R-square value, the R-square change value of 0.015 is the difference between the R-squares for these two models. And you can see that the f-test, which is used to test the difference in R-squares between those two models, we have statistical significance. So by virtue of adding in that cubed interest variable after we've centered it, we've actually increased our predictive power a significant amount. So as you can see then that when we compare then models 2 and model 3, you can see that by adding in that cubed variable, we account for an additional 1.5% of the variation. It's not much, but we do have statistical significance in that case. So another thing I do want to point out too is that we could have accomplished a lot of this too by kind of going down to the coefficients table, and if we didn't want to focus in on the R-square changes and so forth, we could just as easily test these or make our comparisons by looking at the highest or the significance test for the highest powered variable. So if you look down here, you got for model 2 right here, here is the regression coefficient for the squared interest variable, and you can see we have our significance test that's given right here. And basically this test is equivalent to the f-test of the change in r-squared between model 1 and model 2. So if this test is significant, at least with respect to model 2, then that's going to indicate that by virtue of adding in that squared interest variable, we are gaining predictive power. And then if we look at model 3 right here, if we look at the test results for the cubed interest variable right here, there's our regression slope for that cubed interest variable. That is the same as the f-test of the change in r-squared between model 2 and model 3. And so you can see right here that we gain additional explanatory power by virtue of adding in that cubed interest variable. So either way will work, but I will say that I kind of mentioned earlier that there is kind of an easier approach than kind of going through and kind of doing all of this work. I still would recommend and strongly encourage that you would center your interest variable in this particular case, but whatever your x variable is, before you do what I'm about to show you. So the other option, which is actually going to be a little bit simpler, is to go through Analyze, Regression, and then go down to Curve Estimation. So if I click on Curve Estimation, then what I can do, I'm going to kind of reset this for you so you can see it in action. We'll move the achievement variable to the dependent variable box. We'll move the centered interest variable to this box right here. And you've got various models that you can select. So by default we have linear selected, but I'm going to select quadratic and cubic next. So I'm going to select those guys. And next, I'm going to make sure to click on Display ANOVA Table. So make sure that you do that too. So we're going to be testing a linear model, quadratic model, and a cubic model, and we want to make sure that we've selected the ANOVA table. And once again, I can't focus on this enough or encourage you enough. Make sure that that interest variable, or whatever your x variable is, that you've centered it prior to doing using this approach right here. So we'll click on OK. And now you'll see that we've got our different models that we just ran, but it's kind of generated all at once. So you'll see first off it starts out with a linear function. So in this case there's our simple linear regression with the centered interest variable as a predictor. There's the ANOVA result, and then our coefficients that we started out with, and then also obviously a significance test for, there's the slope that's given right here, and the significance test is a little bit reversed compared to what we started out with in terms of how it's printed out in the output. But nevertheless, you can see that's the linear model. The quadratic model, as you can see right here, we've got the r-squared value of 0.906. This is the fit of that model. And then if you look in the coefficients table, you've got the centered interest variable and then also the squared variable. If you remember what I said just a couple of minutes ago when we were looking at the coefficients table after we kind of performed that hierarchical regression, we can use this test of that higher order term in order to determine if the r-squared change is statistically significant. And you can see that the result right here is the same as the result that we had for the squared interest variable in model 2 when we ran that previously. Then if we scroll down a little bit further, we've got cubic, and so there's the r-squared value for this particular model, and there's the f-test testing the overall fit of that model. And once again, if we look at the cubed variable right here, we have the regression coefficient and then the test, the significance test for that regression coefficient. And so as I said before, we can take that test associated with the coefficient for the highest order term and basically test this out, and this would give us the test of that particular model, and basically the change in r-squared between the quadratic model and the cubic model. We can test that out by looking at this particular test result right here. So that's basically all there is to it, and you can see that this result is the same as is what we saw when we were testing the difference between Model 2 and Model 3 previously. So now we'll scroll down a little bit further, and you can see that you can also kind of visualize the data a little bit. You can see that the program has already printed out kind of different fits of different models to the data. You've got the linear model that is reflected right here in this line that's given, and then you've got kind of the quadratic and cubics that are given as well. So there's the quadratic that's given right here, and here's the cubic that's given right there. So this may be kind of a long video and so forth, but I really kind of wanted to spend a little bit of time kind of unpacking what these different concepts mean. As I said before, it's not really totally necessary that you would need to kind of manually do the hierarchical multiple regression as I did. Ultimately, we landed on this curve estimation approach that is very simple. You probably are not going to be able to do quite the same things in the same ways with the if you're running a multiple regression where you've got additional covariates. I mean, you wouldn't be able to use the curve estimation in the same way as we did right here. But you still can utilize the hierarchical approach that I kind of went over earlier. So at any rate, that is going to kind of wrap up this video presentation, and I appreciate you watching.